Hello everyone, welcome to the video solution for physics. This is Cambridge International Exam, is Physics Paper 2, May-June exam 2017. Let's start. Question number 5. Define the frequency of sound waves. So frequency, general concept of frequency is number of cycles per unit time or number of oscillations per unit time, number of waves generated per unit time. So you can define frequency as number of oscillation or sound waves generated in unit time. It is called a frequency. And part B is a sound wave travels through air. Describe the motion of air particles relative to the direction of the travel of the sound waves. So what happened? Suppose this is the particles of medium, and if waves is traveling, let's suppose rightward, then every particles of the medium oscillates parallel to the direction of motion of the wave. So oscillation of particles also parallel to the direction of motion of travel. So you can write that the air particles oscillates parallel to the direction of travel. Part C, the sound wave emitted from the horn of a stationary car is detected with a microphone and displayed on a cathode ray oscilloscope, CRO, as shown in the figure. The y-axis setting is 5 millivolt per centimeter and the time-based setting is 0.5 millisecond centimeter inverse. Remember, in a CRO, horizontal axis is always time axis and the vertical is voltage axis. So use figure 5.1 to determine the frequency of the sound waves. And if you see, this is square from here till here, the one square is equal to 1 centimeter by 1 centimeter. That means we need to find the frequency. So frequency is 1 upon time, capital T. Capital T is the time period, time for one cycle. So we need to figure out where the one cycle is completed. So starting from that point and till here, this is one wave, and in this one wave we have a 1, 2, 3 and 4. So 4 boxes are there. So the time period for this wave would be equal to, so T would be equal to, one box is 0.5 times 10 to the power minus 3, because it is millisecond, that's why 10 to the power minus 3, times we have a 4 boxes for one wave, so times 4. That means the time period is equal to 2 10 to the power minus 3 second, and frequency is 1 upon T. So if you take the reciprocal of the time period, so frequency would be equal to 500 Hertz. This is the frequency of the sound wave. Part 2, the horn of the car sounds continuously. Describe the changes to the trace seen on the CRO as the car travels at a constant speed directly toward the stationary microphone. So if source moves towards the listener or toward the receiver, so receiver or the microphone receives high pitch in shorter interval of time. So you can say that high pitch means the loudness or the pitch would be high, frequency will be higher. That means the amplitude would be higher. It's just I'm writing a symbol and you must write higher in a less time period or less time. So time would be less. And what if it is moving directly away from a stationary microphone? If it is moving away, then it will be receiving low pitch sound, so amplitude will be decrease. and then time to receive the wave will be increase. Question number 6. Interference fringes may be observed using a light-emitting laser to illuminate a double slit. The double slit acts as two sources of light. Explain the part played by diffraction in the production of fringes. Now, if you recall, diffraction is when a wave passes through some gap. If a wave is passing through, this is the wave coming, right? This is the gap. So when the wave passes through this gap, it is spread out. So this is the diffraction behavior. So now we have two slits. So when wave passes through two slits, they get diffracted, and after diffraction they superpose and then gives us fringes and produce interference pattern. Next, the reason why a double slit is used rather than two separate sources of the light. We are using double slit because we split a single beam of light into two in order to get coherent waves or coherent beam of light. Because if we use two separate sources, they will not be coherent. That's why we use double slit and split a single light into two with the help of double slits. Part B, a laser emitting light of a single wavelength is used to illuminate slits S1 and S2 as shown in figure 6.1. So this is the laser light. These are two slits S1 and S2. Distance between two slits is 0.48 millimeter. Distance between slits to the screen is 2.4 and a screen. Okay. An interference pattern is observed on the screen AB. The separation of slits is 0.48 and the slits are 2.4 meter away. The distance on the screen across 16 fringes is 36 millimeter as illustrated in figure 6.2. Okay, so we have a 16 fringes here in 36 millimeter distance. Calculate the wavelength of the light emitted by laser. So we have two slits, right? Okay, we have two slits like this, S1 and S2, and the distance, this distance is generally we use letter A, and this is the screen, and we have a distance. I'm using capital D for that distance, and this is the center of the screen. And if we have somewhere here, if we have a single fringe, this is fringe, then fringe width x or delta x, whatever you say, the fringe width x, A, D, and the wavelength can be related with the equation x is equal to fringe width is equal to lambda capital D upon A. So this is the relation between four quantities, D, distance to the screen, fringe width, slits distance, and the wavelength. And in our question we need to find the wavelength. Clearly, if we need to find the wavelength, then wavelength lambda would be equal to XA upon D. We have A, which is this, and we have D, but what about X? X is the fringe width of only one fringe. We have a 16 fringes and distance 36 millimeter. That means X would be equal to 36 millimeter, so 10 to the power minus 3 divided by 16. This is X, and now we can apply the approach. So x is 36 into 10 to the power minus 3 divided by 16 into a, and a is 0.48, 0.48 into 10 to the power minus 3, because again millimeter, divided by capital D, distance, which is 2.4. Once you simplify this, lambda would be equal to 4.57, 4.5, not 7, 4.5 into 10 to the power minus 7 meter. This is the wavelength of the light. Part C, two dippers D1 and D2 are used to produce identical waves on the surface of water, as illustrated in figure 6.3. So these are two dippers D1 and D2. They are producing two waves, and both waves are going towards point P, and where they meet or superpose, produce interference pattern. Point P is 7.2 centimeter from D1 and 11.2 centimeter from D2. The wavelength of the wave is 1.6 centimeter. The phase difference between the two waves produced at D1 D2 is 0. State and explain what is observed at P. Okay, we know that two waves are coming at point P from two coherent sources. That means we can expect interference at point P, and the type of interference here depends on path difference. Path difference. So first we need to calculate the path difference between these two waves. So path difference, in short, I am writing P into D. Path difference is equal to 11.2 minus 7.2. So path difference will be 2 get cancelled, 11 minus 4 centimeter. So this is the path difference, and now you compare this path difference with the wavelength. That means 4 divided by 1.6, and then answer you will get here is 2.5. That means the path difference is 2.5 lambda, or you can say 5 by 2 lambda, odd multiple of the wavelength, half of the wavelength. That means we can expect destructive interference. So no ripples are seen, no waves are produced at point P. So there is no wave, nothing happens at wave, or there is no movement at P. Part 2, state and explain the effect on the answer to CI if the apparatus is changed so that separately the phase difference between the D1 and D2 is 180 degree. So what happened if because remember what is happening, we know that path difference is 5 by 2 lambda, and if you recall, if you see the previous question, they are saying that initially we have a phase difference 0. So phase difference was 0 in previous case, and the path difference was 5 by 2 lambda. That's why we had a constructive interference previously. But now at the start, both waves already have a phase difference of 180 degree, and at that phase difference, when the two waves reach at point P with that path difference, then the condition of interference revert. At that moment, we see that the water is producing wave at point P. So we see a ripple producing and water movement. So we have a constructive interference in this first case. The intensity of the wave from D1 is less than the intensity of that from D2. That means if you change the intensity of any one of the wave, we still have a constructive interference or a destructive interference, whatever the situation is. But in this case, because they are saying we are changing separately, that means we assume that the first case, initially there was a phase difference 0 between d1 and d2, and the path difference is 5 by 2 lambda. So there will not be a complete cancellation or complete destructive interference. So we will see movement. We will see movement in the water. Question number 7. Define electromotive force (EMF) of a cell. So EMF of a cell is a energy transfer to unit charge, or an energy transfer to per coulomb charge from some other form to to generally in electrical form. So this generally happens inside the battery. So the chemical energy inside converts into electrical energy. So energy transfer to unit charge. Part B, a cell C of EMF 1.5 volt and internal resistance 0.2 ohm is connected in series with the resistors X and Y as shown in figure 7.1. So this is a circuit, internal resistance, variable resistance, and X. The X is a constant and Y can be varied. The resistance of Y is varied from 0 to 8 ohm. State and explain the variation in the potential difference PD between the point A and B, terminal potential difference across C. Numerical values are not required. Clearly, if you see the relation between EMF and the and the terminal potential difference, which is E is equal to V plus IR, and if you rearrange this equation for terminal potential difference, V is equal to E minus IR. Now, what happens if you vary value of Y from 0 to 8? As Y is increased, when Y is increased, then amount of current is going to decrease because you are increasing resistance. So amount of current flowing in the circuit is going to decrease. Therefore, IR, which is this term in the equation, IR, and it is in fact a lost volt inside around the internal resistance. So due to decrease in the current, overall product, that means IR is going to decrease. If IR is decreased, it is subtracting from that term, that means V must be increased. So terminal potential difference is going to increase if Y is increased. The resistance of Y is set to 6 ohm. The current in the circuit is 0.18 ampere. Calculate the resistance of X, the potential difference between point A and B, and the efficiency of the cell. We need to see the circuit diagram. This is a circuit given in a previous question. Clearly, you can see that if you need to find the resistance X. So, if you consider that this is your power source alone, and we have three resistances. This is the internal resistance R, this is X, and this is Y. These three resistances are connected in series in a series circuit with this power supply. So you can say that this is for solution 1, that if EMF of a cell should be equal to voltage across internal resistance plus voltage drop across Y plus voltage across X, meaning you can say that VR is IR plus VY is I into Y plus Vx is I into X. So you can take y common, so E is equal to I times R plus y plus x. Clearly, you have I, which is 0.18. You have R in the diagram, 0.2. And Y we set as a 6 ohm. And EMF is 1.5. And you substitute these values and you can figure out value of X. So X would be equal to 2.1 ohm. Part 2, find the terminal potential difference across A and B. So terminal potential difference across A and B is V equal to, this is 2, V is equal to E minus IR. Again, you have all the values, E, I and R. E is 1.5, I is 0.18, R is 0.2. So if you're plugging the value, and you can find V is equal to 1.46 volt. This is the terminal potential difference. And the third is efficiency. And efficiency, E is output power upon input power. And in general, power is V into I. In this case, you can say that output power is terminal potential difference into current divided by input is EMF into I. So I is same, so I gets cancelled, meaning V upon E. So yes, just don't be confused with this E and this E. It's better if I change the symbol for this E. So this E dash I am using for efficiency, and this E is EMF. Okay, so E dash is equal to voltage terminal potential difference 1.46 divided by EMF. So this is 1.5, and the number that you get here is 0.97, 0.97. If you multiply by 100, so it will be 97, around 97% something. You can check your numbers. Question number 8. Describe two differences between the decay of a nucleus that emits beta negative particle and decay of a nucleus that emits beta positive particle. Differences. Okay, first you must remember that beta negative means you have electron, the normal electron that we already know with the negative charge, and beta positive mean we have anti-electron, which generally we call positron. So the first difference is in beta negative particle, neutron decays into proton. So neutron decays into proton along with emission of beta particle, beta negative, and this is the first difference. Neutron is decaying into proton along with beta negative. And the second difference is we have emission of anti-electron neutrino. Emission of anti-electron neutrino from this decay. So this is these are two differences in beta negative. And what about for beta positive? So in beta positive, we have a proton decaying into neutron along with emission of beta positive, but along with the beta positive, we have emission of electron neutrino. So this is the difference. For beta negative, we have anti-electron neutrino. For beta positive, we have electron neutrino emission. Yes. Part B, in a simple quark model, there are three types of quark. State the composition of the proton and the neutron in terms of these three quarks. So proton consists of three quarks. It is a baryon, so it is consist of two up and one down quark, so UUD, and the neutron consists of two down and one up quark, so you can say DDU. These are the composition. Thank you very much for this video. I hope you enjoyed it. Have a nice time. See you in the next one.